probably. If you're watching the Olympics on TV or whatever, you see a figure skater doing this, right? So if you are a figure skater and you're balanced on a little tiny point of metal on ice, that is about as net torque free from the outside world as you can get, right? So in that system, the rotational inertia is decreased when you pull your arms in, and you will rotate faster in response. Now this system is also one in which the net force is 0 as a whole, so my center of mass stays put. Because obviously, the force of gravity pulls down on me, but the floor just holds me up. So the net force happens to be 0 in this system as well, but that doesn't have to be the case, because another example where you see this is not for a figure skater, but for a diver. So let's take a look at that. So let's say you have a diving board, and you have someone that jumps off of it, like so. Well, as we talked about, the net force and net torque are independent things, generally speaking. Now, there is definitely a net force on this diver, okay? That is what makes them go toward the ground, right, or toward the water. The net force on the diver is most certainly not 0. That is what guides them in the good old trajectory. Their center of mass is going to have to follow that classic trajectory from our homework, 3? But the force of gravity also pulls at their center of mass, which is the pivot, but there could be rotation around it, okay? The net torque is 0, okay, because the force of gravity has no leverage. Has no leverage against the center of mass. That's because it pulls at the center of mass. So you are still under the same physical laws as the ice skater. You can still tuck your arms and legs in and spin faster, or spread them out and spin slower, okay? So same deal, if you tuck in like this, if you have any, I guess I can try to draw this. Not bad for me, okay? So if you tuck your arms and legs in, you'll reduce your rotational inertia and you will spin faster so that your angular momentum is conserved. And if you're an acrobat or a diver, you have some kind of sense of where you know, how much time is it going to take for you to hit the ground or whatever, or hit the water, and adjust this so that you can not, belly flop in the Olympics or whatever, okay? So notice that the operative thing is that the net torque is 0. That is when angular momentum is conserved. Whether or not the net force is 0 is immaterial, right? This system, the net force happened to be 0, but in this one it isn't. Okay? Are there any questions on that example before I move forward? Okay, so now let's actually do a kind of a similar thing to what we used to do over here, which is that we have 2 objects colliding, right? So 2 objects interacting. Let's have 2 independently rotatable objects. Me and the turntable will be 1, so we hopefully stay together. And then I'll have a second object, which will be this bicycle wheel. So that'll kind of be like our 2 objects in the system. I guess it's example 3. I forgot to label this one as example 2. So let me draw it from the top view just because it's more easy that way. Here's me on the turntable, like that, and I'm holding the wheel. And let's say initially the wheel is spinning, but I'm not. I'll kind of hold it like that. Those are arms. If you don't see what that's supposed to be. All right. So let me label these. Me and the turntable will be object 1, and joining me will be object 2, the bicycle wheel, an independently rotating thing. So let's take stock, angular momentum of the system. L1 plus L2. Of course, have to account for all members of my system. And I do want to include both of them in the system because I will be torquing that wheel and it will be torquing me. So the internal torques, we want to bury them inside. That way, the net external torque on the system is 0. To the extent that air resistance can be neglected and the pivot itself is relatively frictionless. By the way, that's the big code word you're looking for in these problems. If you see frictionless pivot, you should automatically thinking, okay, that's how it's going to be justifiably the net torque being 0 from outside. The system is left alone from the outside world. Anything can happen within the system. It's just going to trade angular momentum between the members, not change the total. So initially, I am not going to be spinning, so I have no angular momentum. And then the wheel, from this perspective, is spinning counterclockwise, which we usually call what? Plus. So that means that the system initially will have overall counterclockwise angular momentum. That, of course, is due entirely to the wheel because I am not contributing. Then, here's going to be the final state of the system. I'm going to just flip the wheel around. Now, flipping the wheel around may not seem like a big deal, but this is a vector. So if you change the, if I flip it around, it goes from being counterclockwise, right? If you flip it, it spins clockwise. It's like reversing the direction. And that matters with the vector, right? That is a change. So I'm going to flip the wheel around so that now it spins like this. Oh, that came out even worse. It's supposed to be the same picture with the wheel going in the direction. So let's take a look. So flipping the wheel around is basically akin to reversing its rotation direction. And so now that'll be negative, right? Negative is clockwise. But remember, we are in a system where the angular momentum has to be conserved. So whatever positive value it had, it still better have it. So something has to give. There's no way to make this equate otherwise. What must be the angular momentum that I have? Is it plus or minus? It's going to have to be plus. And in fact, it's going to have to be plus to compensate, more than compensate for the negative angular momentum in the other one, right? So that means that I will start spinning in the original direction that the wheel was spinning in. So let's try it. I'll rotate this thing like this. It's rotating like this. I'll get on here. And whatever happens from here, the angular momentum is conserved. So if I flip the wheel around, I spin in the original direction. Yes? We can trade it back and forth, but the total has to remain the same as soon as I step onto the platform. Now you might ask, if this has to be bigger than this, why don't I start spinning around faster? Well, remember that the angular momentum is two pieces, right? I have a much easier time with my large rotational inertia. I don't have to really spin that fast to more than make up for the wheel. Okay? Once I get on the platform, I can torque the wheel can torque me back, right? It's kind of like the Newton's third law in the rotational world. I torque it, it torques me. We can trade angular momentum back and forth all day, but the total will remain the same. I'll show you some other scenarios. Okay? I can decide to steal it all. Here I have it all. I don't have to spin very fast. Okay, now I have it. I can give it all back to the wheel. right? You trade it back and forth all day. The total doesn't change. Okay? So whatever happens on the platform, we're trading angular momentum back and forth, but the total can't change. I guess another thing I can show you, if I get on with no angular momentum, oh, if I can stop not spinning. If I get on, why is this floor get slanted or something? I don't know why I'm spinning spontaneously. Okay, I guess the floor is just tilted. So, what? Yeah, all right. Well, ignoring that for a second, let's say that the wheel's not spinning, I'm not spinning. So how much angular momentum does the system have? Zero. So it's got to stay zero. So if I start spinning this way, what am I going to have to do? Spin the other way, so the total can still be zero, right? Notice that I'm, of course, rotating a lot slower than the wheel is because I times omega has to be the thing that's equal and opposite. That's basically the rotational version of those two ice skaters pushing off each other. Remember that one? They're just standing there, they push off each other. So they push off with equal and opposite momentum. But since one is more massive, it doesn't have to go as fast, right? So that's just the rotational version of that. Okay, so that's angular momentum. Are there any questions? Yeah?
In example 2, did you need external net torque is 0? Or?
Yes, net external torque and net external force. I meant that for all of these. Okay, any other questions on this? Okay, so again, if you feel like trying one or both, you're welcome to it at your own risk, of course. So that, what I just talked about today, plus the 2 simple harmonic motion lectures that I posted for you, that will form the entirety of your homework 10. I'm going to see how much in the next 10 minutes I can get done for start to crack open homework 11, which will be all on fluids, okay? Okay, so fluids, just want to go through some very basic things first. These are not even particularly physics. You've probably seen these in some form. Density. So density, I use the Greek letter rho. It kind of looks like a round off P. It's the mass over the volume. So this is often useful for identifying what things are made out of. You may have used it for that, I'm not sure. But as far as density goes, I want to talk about the difference between solids, liquids, and gases. Okay. Now solids, obviously they have, they can have shape, right? So these often are in fixed shapes. Whereas liquids and gases are really, kind of just depends on the shape of the container. And so for our purposes, liquids and gases are what we mean when we talk about fluids. So we, of course, talk about liquids as most of the time as being fluids, but gases are also behave in the same way. Okay? So basically, they just, there's nothing holding them together, so they tend to take the shape of their containers and flow. Okay? Solid doesn't really flow. Now, there is going to be a distinction we have to make in terms of density, because solids and liquids we take as approximately incompressible, which means they have approximately fixed density. So you can look up, for instance, what's the density of lead or aluminum or things like that. Hopefully those things don't surprise you, that they have a certain characteristic density. They have a certain arrangement of their atoms, that their spacing that they like, which determines how much volume a certain amount of mass takes up. It may be more surprising for you to think of a liquid that way. So we tend to think of liquids as kind of not really so stiff, but if you put, say, take like a 2-liter bottle of soda that you buy from the store, that thing is as hard as a rock. And that has nothing to do with the plastic container, which you can easily crush once you've drank all the soda. Okay, it has to do with the liquid itself. You can't take it and put it into a smaller space than it already exists in without a considerable amount of trouble. For our purposes, we consider these as fixed density. Okay? For water, for instance, liquid water, we take its density as 1,000 kilograms per meter cubed. You can't negotiate that. A cubic meter of water has 1,000 kilograms of mass in it. That's our SI unit, of course. You may be used to 1 gram per cubic centimeter, which is often used in chemistry, which is, of course, you can convert from one to the other if you don't believe me that they're the same. Gases are the only ones where we can take them as compressible. So, for instance, the air in this room is 1.2 kilograms per meter cubed, but you can easily negotiate that. Okay? What you do is you grab yourself a container, you trap some air in it, and of course a gas is mostly empty space, so you can easily get that empty space to be a little smaller. You can compress it, and you can make the same mass of air molecules go into a smaller volume, and then you will have a larger density than that. You can easily negotiate the density of gases. Okay? So we really have two different kinds of fluids. We have incompressible fluids, which are liquids, and compressible fluids, which are gases. The compressible fluid is the most annoying one because we have to worry about its density changing out from underneath it. So generally speaking, we'll focus on liquids. Occasionally, we'll bring gases up, and we'll say, yeah, gases pretty much work like this too. And if we want to do a calculation, we're going to have to assume that the density doesn't change out from underneath us, even though in many circumstances it might. So that's a little bit on density. And then let's say a few brief words about pressure before we knock off for the day. Oh, and I forgot also, our number one substitution that we're going to make is for mass. So of course, mass has been with us since homework 4 as a particular quantity. You can substitute density times volume for it. Pressure. Pressure is defined as force per area. It's the amount of force applied over a given area. For us, the SI units are going to be newtons per square meter. So our units for force are newtons, our units for area are square meters. This gets its own name. This is called a Pascal, or PA for short. So SI units are pascals. There are many other units for pressure that you may have seen, none of which are SI. First, for instance, if our atmospheric pressure at sea level is 1.013 times 10 to the 5th pascals, which, ignoring some of the refinements, is about 100,000. So that's how much force per area is acting on you right now from the atmosphere. This is also called 1 atmosphere. So you can tell that's a very human constructed thing. Let's call the pressure we're at 1. Okay. Other things you may see, bars. Bars, kilobars, that's unit of pressure, that's not SI. You might see pounds per square inch, or PSI, that's also pressure. You might see millimeters of mercury, or torr, that's also a unit of pressure, but the only unit of pressure is pascals, which that's the only SI unit. Okay. Let's talk a little bit about why you'd want to define this quantity in the first place. Why not just talk about force? Well, there's a lot of things where pressure is more important. It's not how much total force you're experiencing, it's the amount of force distributed over a certain area. So, for instance, if we compare like a syringe to a punch, if we apply the same amount of force with both of those things, obviously something very different happens. Okay? A syringe is distributed over a very small area, whereas a punch is not, and so the pressure will be different. The syringe will exert a lot of pressure and will easily exceed the breaking pressure of your skin. So your skin has a characteristic breaking pressure, not a breaking force, but a characteristic breaking pressure. The punch is applied over a much larger area, so it does not exert as much pressure. Okay? So that's one example only of why you want to care about pressure, not just how much force is exerted, but over what area is that force distributed. That being said, one of our most common substitutions is once again for force. Okay? So force has been with us since homework 4. One of the substitutions we'll make is pressure times area. The only other thing that I will add here before we knock off is that the direction of the force is always, let's say I have something here, I have a pressure on this side, P1. Basically, that comes from the thing wanting to get over here, and because it can't, it bounces off, and it exerts a force like this. You could also have pressure on the other side, and again, those air molecules bouncing off this, whatever this is, this membrane, because they can't get over there, they exert a force like this. So basically, the force is not inward or outward or left or right. It's the force, it just acts to try to increase the volume of the material. Basically, pressure comes about as a result of the material wanting to get into a space where it isn't already, and because it turns back, it exerts a force there instead. So it exerts a force, so you can't, because it can't get there. And here, we can, of course, talk about the net force. The net force here is going to be the competition between the two pressures on either side. Okay? So assuming they're both pushing on the same pressure area A, I can factor that out, and it becomes a competition between the two pressures. Okay? So let's call it a day there, and we'll pick up new material, I guess, a week from today, since we have the exam on Thursday.